Hello everyone, welcome to Lab 6, Design and Characterization of Transmission Line using CST. Today in this lab, we will see a very common form of transmission line, a type of cable called coaxial cable. And we will use CST Microwave Studio. We'll design a part of coaxial cable with having two ports at the both ends, and we'll study on S parameters and also how electromagnetic field propagates along the coaxial cable. So before we start, we need to mention one thing, that we need to understand the structure of a coaxial cable. So to understand that, let's move to the page number 3 first. You see there are different layers in the coaxial cable. The inner white part is called the inner conductor, which is made up of copper annealed with a radius of A. Then we are having the dielectric layer, which is a yellowish or grayish part, and we are having this arrow is called the outer radius, and which is B. And finally, again, the white part surrounding the dielectric part is called the outer conductor. This is also made up of copper annealed. So we are having like two conductor layers, which is inner conductor and the outer conductor. In between them, there is the dielectric layer, which is made up of a material called PTFE. And finally, we're having this protective layer. During the design procedure, we will start from the inner core or inner conductor, then we will put the dielectric layer, and then finally we'll end up with the outer conductor layer. So I am here because we are given some parameters already. If you go back to the previous page, you see that these are the design specification of the coaxial cable. You see the name of the material we just mentioned, which is PTFE, polytetrafluoroethylene, and we are having the resistivity, permittivity, which is 2.1. We mentioned that copper annealed, the conductor material. We're having some more parameters such as conductivity of the copper, and we are given only the inner conductor radius, which is, let's go back to the cross section again, only this parameter, which is A. So that means we are not given B. Well, this was done purposefully because if you go back to the pre-left section, we are having some questions to answer, and for this part we have to use the MATLAB coding, a small short of MATLAB coding. This is not going to be a very big one. I mean, this is a very simple MATLAB coding. So I'm saying this because, as we mentioned, that we are only given the inner conductor, not the outer conductor, which is P. So but we need both of it for designing the coaxial cable using the CST. So before you jump in to the CST design procedure, or design section, let's look at these questions first. Provide a plot of the characteristic impedance of the coaxial cable versus the outer radius of the dielectric. So that means the outer radius is an unknown variable or unknown parameter. We know the characteristic impedance, which is 50 ohm. So that means what you have to do with MATLAB coding, you have to derive a relationship between that shows the relationship between the characteristic impedance and the outer radius. So that means if you let me show you something. I have got the results though, but you're gonna do that by yourself. If you look at the diagram, you see this is a plot between outer radius and the characteristic impedance. And once you're done with the plot, you can easily get the value of outer radius exactly for 50 ohm characteristic impedance, which is 0.000335 or 0.335 millimeter, since this is in meter. So you have to derive this plot. Now the question is how. Let's go back to the tutorial. There are some formulas here, which is a little bit of theoretical part of any transmission line. This might have been covered, very likely, that in your theoretical part. Whenever you know something about the transmission line, you have heard about those parameters. You're having series resistor, inductor series, then shunt capacitance. You are having this conductance value, capacitance, inductance, and resistance. You see, in all of the formula, some things are given, some things are not. Let's say conductivity, which is given from the table that we have seen before. You see the conductivity here, and there are more. If you can just have a look, you see the frequency of operation, which I didn't mention that this is going to be 1.5 gigahertz. So let's go back to the formula. This is this is B and A. B is the outer radius, A is the inner radius. A is given, B isn't. You see the permittivity, which is 2.1, given in the table above, and you see the permeability and other parameters. Okay. So now the question is, how do you plot the plot that I mentioned, which I have shown here, the characteristic impedance versus outer radius. Let's go back to the tutorial again, and you see at the page number 5, these are two equations. So if you look at this equation, you see the Z0 and the relationship between Z0 and the B and A. You are given with the epsilon R, which is 2.1. You are given A, but you are not given B. So that means B is an unknown variable, which I mentioned before, that B is something that you have to measure, you have to calculate or determine, so that you can use that in the CST. Now that this is the equation that shows the relationship between Z0 and the outer radius, you know the EA. So that means just well, using this formula, you can use this formula in MATLAB and just formulating this, structuring this equation in MATLAB, and you can easily make a plot between Z0 and B, which is this one. So this is what you are asked for. Provide a plot of the characteristic impedance of the coaxial cable versus the outer radius of the dielectric, which is done. So once you are done simulating this equation in MATLAB, remember Z0 is 50, A is 0.1, which is given already, epsilon R is 2.1, and you can get this plot. Once you are done with this plot, you pick this value right at 50 ohm, and you pick the respective value, which is 3.5 meter, or 3. If I want to be really precise, it's going to be like 0.000335. That means you are done measuring the outer radius, which is 0.335 meter. So we are done with all the parameters which will be required during the CST design. Now you have to answer a few more questions. If you go back to the pre-lab section using the MATLAB. Comment on how the characteristic impedance of the coaxial cable varies as the outer radius of dielectric is increased. Well, that is up to you. You have to comment how the characteristic or this trend is changing between these parameters. Okay, and then once you have determined the required radius for Z0 50, which we have done, plot Z0 versus frequency ranging from 500 to 2.5 gigahertz. So that means now that you are done with determination of the radius, use this formula. Let's go back to the page number 5. You see, this formula will be required now. So you see that omega, which is 2 pi f, that means, again, you know the Z0 value. Now the question is, how can you get those values? R prime, G prime, L prime, and C prime. Well, you are done with B, you are done with A. That means you can easily get those values. Okay, and once done with those values, it's easy to get the value. Oh, okay, you know the Z0 value. So use this form, and only the omega is a variable here. Again, just like this equation, use this equation in your MATLAB coding and just get a plot, and you will get something like this. Okay, this is the relationship between characteristic impedance and the frequency. Remember, omega is the angular frequency. If you know the omega frequency, you can know the omega, which is twice pi f. So the range is 500 or 0.5 gigahertz to 2.5 megahertz. And have some comment on this. Just use your common sense or use your knowledge. It doesn't have to be really accurate. Okay, just have your comment, whatever you understand. So we are done with the pre-lab section. We are done with determining the parameter of associated parameter of the coaxial cable. Let's move on to the CST design procedure part. For this, let's go back to the CST software. Remember, our frequency range is 0.5 to 2.5 gigahertz. So let's go to File, New Template, Microwave and RF Optical Antennas. We'll stay here because coaxial cable is a form of waveguide. We'll stay there. Time domain. We'll not change anything here. This is pretty handy. Not to change later, rather changing it here is better. Okay, so try to change it here so that you don't have to go to those setup again before you run the simulation. So it's the range, which 0.5 to 2.5 gigahertz. Okay, this is a good habit to check on those things just in case if you need those. And the default center frequency is 1.5, and this is the required frequency. If you see this is something else, change that to 1.5 because our coaxial cable will be characterized or analyzed at 1.5 gigahertz frequency. So if we change that frequency, make sure this is 1.5 gigahertz frequency. Okay, so go to next, and we are done with the pre-setup of the CST, and let's start. Let's start designing the coaxial cable. For this, let's go to modeling. Well, the coaxial cable looks like a cylindrical shape. So that means for each layer, such as inner core, dielectric, and the outer radius, the shielding, everything looks like cylindrical. And remember, those are of the same length, which is 10 millimeters here. So we will stick to the same length. However, we'll change the radius and also the materials. Let's go back to the CST. So pick up one cylinder. You don't have to click anywhere, just press escape. Okay, name it. We'll start from the inner core. So name it inner core. don't change the orientation, outer radius and inner radius. Okay, it looks like this is a solid thing. Okay, so the inner core is solid, it doesn't have any hollow inside it, so that means we are not having any inner radius. It will start straight away from 0 center. But however, outer radius is going to be 1.1 millimeter, but don't put that 0.1 millimeter here. This is a smart approach to parameterize the thing. So let's just define a variable. Let's just use a, which is the case of which has been used in the tutorial as well. So we will put the value later, and there is a benefit of using these parameters rather than using the values. I will tell that in a bit. And you know, Z-man, just put minus L over 2 and L over 2, L for length. Now why am I doing that? Because, well, it could have put like 0 and L. It makes this, it means this, I mean, this is the same thing. I mean, I'm trying to say that if you press here 0 and if you press L, this makes sense, same thing. So I am pretty much comfortable with putting this so that we are having the 0 reference in most of the times. Okay, so now that we haven't put any value here, it will ask for the value. Okay, don't forget to change the material, which is the copper anode load. So A, as we mentioned, that this is 0.1. L, this is 10 millimeter. I guess we are done with the inner conductor. So going back to that parameterized things, you see there is a short list here of those parameters that we have defined. So if you suppose, although you don't need to change that dimension here, but for a complicated design, let's say you want to change the length of the this portion of this coaxial cable, you normally we are habituated going back to this menu here or trees here, and then you have to click this thing, you have to double click here, and then you change that thing here. Well, if you just parameterize the thing, this will be listed here and you don't have to go over all those steps every time. Just put a value here and update it. Press enter and just parameter and press F7. It would be gone. It would be done. This is a very smart approach, and this is a very handy approach. Okay. Anyway, so we are not changing this. We are just staying with 10. Okay. Now we are done in the inner part or inner core. Now we will design the tertial, which is the dielectric layer. Again, as I mentioned, this is also a cylindrical shape. Press escape, name it. Electric. We are not changing the orientation. This time we have started from A, 0, and then A, and then B. So outer radius is B, which we have already determined using that MATLAB coding, remember? And remember, we will start from here. So in this case, this is the center. This length is A, and we will go after that. So in this case, our inner radius will start from A, and outer radius will go up until B, which will be somewhere here. A little bit of extension of that from that inner core. You see, I mean, let's go back to the picture. You see, so this is A, So up until this point, this is A. So when we will be designing the dielectric, our lower radius or lower point is A and the upper point is B. That is what is being put here. Okay, so inner radius is A and B. In this case, we don't have to define A, the value, define any value for A because we have already put here 0.1. However, we need to put the value of B. Okay, no x-center change, no y-center change. Z main is always minus L over 2. Excuse me. L over 2. We're not changing the segments, and well, this is the dielectric thing, so we have to change the material and we have to load that from, which is PTFE. Okay, and this is lossy. Don't choose the loss free. We are considering the ideal practical situation, not the ideal condition. So there we go, and press OK. Okay, we have to put the value of B, which we have calculated through the MATLAB simulation again, and we found the value 0.335. Okay, looks nice. Excuse me. So we are done up to this point. Okay, up to B. Now, what about the outer conductor? And since this is not mentioned here, but we have another parameter called C, which we will define pretty soon in CST. Okay, so the question is, in that case, we know the what is the value of that? We have the value of A, we have the value of B, and what is the value of, if assume this is a C, what is the value of the C? Well, we don't have that value, that's true, but we are assuming the thickness of this outer conductor layer is 0.015. Why is that? This is because, well, I'm not being too much detailed on it. This is something called skin effect. Well, this is a very important feature when we are designing any coaxial cable, skin depth, because this conductor carries the electricity. So skin depth determines how the electricity can go or can penetrate through the cross-section area. And this is a very important feature or important characteristic to determine how the electromagnetic wave propagation will propagate, or how will there be a lot of loss or not. So that's, I think, and this is far more sensitive when we are talking about very higher frequency, because for any higher frequency the electricity doesn't really penetrate deep inside, rather it tries to stay around the surface area. In that case, we need more electricity penetration, so that means in that case the design becomes really crucial. However, for lower frequency like 1.5 gigahertz we are talking about in this lab today, we don't have to really be worried about that. A rough calculation using the formula of skin depth for any coaxial cable. If anyone wants to know more about these things, please email me and I can provide him or her with some resources. But however, we are skipping that part just for now, just for today's lab. We are assuming that 0.015 would be an appropriate thickness of this outer conductor for this particular frequency, which is 1.5 gigahertz. So that means from here to here we are 0.335, and the thickness of this outer conductor is 0.015. That means from here to from the center to this layer, let's zoom in a little bit, layer, we are extending from here to here 0.015. That means if the length from A to this periphery, which is C, It has to be 0.335 plus 0.015. That makes up 0.35 altogether. So that means if C is the radius of the outer radius, let's assume this that way. This is the outer radius, and we are going further, which is another radius, and that the whole radius would be from center to this, including the outer radius, outer conductor. It would be 0.335 plus 0.015, in total 0.35. So let's put the value here. So that means let's start designing that outer conductor. Name it outer conductor. Outer radius, let's define as C. Inner radius, in this case this is B minus L over 2. L over 2. Well, this is the conductor, so it's going to be copper annealed. And so C, looking for the value which you have just mentioned, which is 0.35, after calculating the skin depth analysis, skin depth feature, and then press OK. There we go. So excuse me. So now that we are done with the coaxial cable, basic coaxial cable, we have to attach the port here. You see, we are having both waveguide ports here at the both ends, and for this waveguide port, remember we are not we are not using the discrete port here. So that means we have to pick either point or face, but for waveguide port we have to pick the face, not the point. So just click on that thing. You are in the simulation tab. Click on that pick thing, and you have to choose the face of both conductor, not the dielectric. Click on that thing. Click on that again. Right, and then waveguide port. You don't change anything. There we go. You have to repeat the procedure at the other end. Again, you have to zoom in pretty close to see or to check where the faces are. Click on that. Click on that. If you don't find it here, I'm just always clicking on that thing. So if you don't find it here, or if you are just lost here somewhere, just press the down box and you see the pick face. You see all the pick things. Okay, and then click. Again, I'm not changing anything. We're done. Excuse me. Okay, so before your simulation, I'm not sure you will be needing that or not. Just make sure, just a quick check on the field monitor things. Apply. There we go. So now we have to run the simulation. While the simulation will be running, let's have a look at the questions that you are required to answer. The first one is S1 on S21, and also put some comments why they are changing with the frequency. It's pretty understandable, I guess. Your part, you have to answer, you have to have some comments, whatever you understand. And in the port modes, you have to go to the port modes in the 2D and 3D results to have a look what the mode is being used. You have heard about different modes such as TEM, transverse electromagnetic, TM, transverse magnetic, TE, transverse electric. In here, the case of coaxial cable, Normally the electromagnetic propagation happens in the TEM mode, that means transverse electromagnetic mode. We are having both fields orthogonal to each other, and the propagation happens perpendicular to the both fields. So we are not losing any field here, we are having both fields here, and we will check on that soon. Then in the same pattern we can have a look at the line impedance. We should be around 50 ohms. Put some comment on it if you have used the formula and use the CST if they differs from each other. Same goes for wave impedance, and if you see any different, a little bit different value in CST, and from what you have calculated, what you will calculate using this formula, you can have some comments if you like. Excuse me. And then we will see the electric and magnetic field distribution at the cross section as well as along the line, and we will see how the electric and magnetic field propagates along the length. So let's go back to the simulation. The simulation is done. So first thing, that go to the 1D results, click on that S parameter. You see S11, which is the reflection coefficient, and S22. We're having 4 S parameters because we're having 2 ports. So 2 reflection coefficient and 2 transmission coefficients. So they're always, transmission coefficient and reflection coefficient are always opposite to each other. And you know what reflection coefficient and transmission coefficient mean already. We have covered those concepts in our previous labs. And if you want to see the exact value at 1.5 gigahertz, because that is what we are interested in that case, just put a marker and just double click on here, and again double click on the marker, put a value here. You see that's the one. So if you want to see, it's pretty low, the transmission coefficient. That means not low, actually it's pretty high, close to 0. That is what we are expecting. However, if you look at the S11 or S22, they are both same. Put a marker here. Let's see how the value is. So double click on the curve, press escape, double click on the marker. We are interested in 1.5 gigahertz, apply to all. So this is pretty significant, which is minus 51. That is what we want. Okay, so remember, this is the reflection coefficient, so the more negative is better. Okay, and this is the less negative is better. Okay, because we want high maximum transmission. Okay, so we should be able to answer that. And well, let's go to the port modes now. So just click on that plus, click on the plus sign, 2D 3D results. You see the port mode. Yeah. Click on that port 1. Click on electric field. Make sure you look at the cross section, because this is how your port looks like in these options, and how the port is, waveguide is producing your E field and H field. So well, if you can see, if you click on E field, it is going outward. But now if you click on that H field, definitely this is perpendicular or orthogonal to the H field, E field. If you click on port 2, you will see the same. So again, you see the big arrow, which is E field, and if you look at the H field, you see the change. They're orthogonal to each other. Okay. Now, as I was mentioning, you might want to look for more results here, such as line impedance, which is 49.7542, wave impedance, which is 260, and also you might want to check if that varies when you were using the formula, and also make sure you take a picture of those things, since this is part of your lab report. And now let's have a look how the electric and magnetic field propagates along the lane. So go to, sorry about that, go to E field. All you have to click on that 1.5 particularly, and well, it's pretty hard to find, but if you click on that animation, yeah, you see it's kind of like up and down. This is the E field. How about H field? Okay, so this is a way of it propagates the E field. Remember, this is TEM mode, so you see both of the fields. However, they should be orthogonal to each other. To check on that thing, click on H field. So this is the E field again. This is the H field. It's hard to believe, but however, if you look at my cursor, if one field going this way in a sinusoidal form, you see, just think about the screen, up and down. The other should be other field, which is a magnetic field. It should pop out of the screen towards you and should pop in opposite away from you. Okay, it's hard to show here because this is a three-dimensional activity. So yes, this is going towards the screen and out of the screen, going toward the screen and out of the screen. This is how they interact with each other, and that's why the TEM mode is. Okay, so let's close this. Don't forget to take the picture, and probably now we have to move. With one port is waveguide port, another port has to be removed where the discrete port will be used. Okay, so let's do that. Well, I am kind of using the same design, but this is highly recommended that you start another design so that you save this where you have used both waveguide ports at the both ends. You have two waveguide ports at the both ends of the coaxial cable for your future reference, and the other file which you will be opening, I recommend use a separate file and use one end. At the one end is waveguide port, other end should be terminated with a discrete port. Okay. All right. So, well, I'm not gonna do that. Rather, I will just remove one port. So in that case, I'm going into the left side of the screen and go to the ports, and I will remove the port 2. I will just press delete. Yes, this is always okay. The results are gone. Now, instead of that waveguide port, we will use the discrete port. Remember, we have used the discrete port in one of the previous lab. For this, although you should know that, but let me show you that. I mean, go to the simulation, but before that you have to go to the pick function. In that case, well, I think we know the discrete port does not connect to faces, rather they always connect to coins. So that means you have to pick 2 coins from the from both conductor layers. So for these we have to connect this portion and this yellow portion. So well, the best, I mean the safest way to an effective way is to choose the center of this circle. So go to the face center or center of the circle, and now what about this layer? It doesn't have any circle. In that case, you see the edge, the inside edge. Just click, choose any edge center. That should be enough. So we are done with 2 point selection. Now go to the discrete port, and there we go. Apply. There is some issues, I guess. I don't know why the waveguide port is coming still. I have to delete this. Sorry about that. Yep. Okay, I think we are done with the discrete port. So now to go along the tutorial, we are doing right, and we are having waveguide port at port 1, and we are having discrete port at port 2. The reason behind this is that to see if there is any changes in the characterization or in the results. So let's run the simulation now again. So we are done with the simulation. Let's have a look at the questions that what we are told. So in this case, we have to have a look into this picture, because we are talking about the impedance here mostly, and we will basically in this part, the reason behind choosing this discrete port is to having a look how the S parameter changes for different types of impedance setup, and basically we will be using 3 different types of impedance setups, such as 50 ohm, and then a short circuit and an open circuit, and we will have some comments on it, how the S parameters such as transmission and reflection coefficient are changing. Okay, so let's go back to the simulation. Okay, you see the port 3. I'm sorry, I need to mention one thing, that because as you mentioned that we are having some issues with another waveguide port, but don't worry, just assume that this is the port 2. Okay, we cannot change that because otherwise you have to run the simulation here. That's fine, it should be alright. So let's do this. No, we have to design this. We have to run the simulation again. We're fine. Okay, so go to the 1D results and go to this parameter. Well, if you you see, please read 2 in place of 3. Okay, or maybe I will change the things to avoid the confusion. Okay, so the correction is made. The port number 2 is renamed, port number 3 renamed to port number 2 to avoid the confusion. So let's have a look into the S parameter things. You see, this is the remember, although there are 4 S parameters, S11 and S22 are having similar characteristic, and so for S21 and S12. The first one is the reflection coefficient, the second pair is the transmission coefficient. So let's if we just look at the one, it should be alright for reflection coefficient. For now, we will have a look at the S11, and well, you can compare with what you've got when you were using two waveguide ports. That's just an additional task maybe you can consider. But now we will have a look. Our impedance was 50 ohm first for this case. When you look at the table, you see for the 50 ohm. So let's measure the value of S11 at 1.5 gigahertz. For this, you can use the axis marker, or you can use the axis marker, which is this is very common. I mean, you can use the you can use this at card marker, which we have been doing before, but axis marker is another smart way. You don't have to assign the value which you have done in the card marker setup. So this is a pretty good technique. Just click on axis marker and it will show that automatically at 1.5 gigahertz, which is minus 20.86. Okay. I'm not sure this is pretty good or bad, but maybe you can use your understanding. Okay. Definitely, I think this is worse than what you have got in our previous case during the use of both two waveguide ports. Okay. Again, it's a matter of impedance matching. Okay. Remember. Now let's have a look into the transmission coefficient, which is pretty close to 0. So we can see the transmission coefficient is not pretty bad compared to the previous setup. However, the reflection, which were, if I can remember, that was like mine. That's why I told you to save. Save the previous one and use the separate file, since I haven't saved the previous one. But I can remember when I was using the two waveguide ports at both ends, that was minus 51, which is pretty good compared to this. Anyway, now let's look at something more. How about changing these discrete let's go back to this thing. Okay, so how about changing the discrete port impedance different? I mean, we will not keep that as 50 ohm. We have heard about short circuit and open circuit a lot when we in the theory class. How about using those short circuit and open circuit concept in here? But you know, the theoretically for short circuit, the value of the resistance value is kind of 0, and for the open circuit case, this is kind of infinite. But we cannot put any 0 value for the case of CST, or neither we can put any infinite value. However, we have a solution. Let's try with the short circuit things. So in this case, although if we put a value 0, we can put the value 0, but in this case the CST will not accept this value because there has to be some value for impedance. So this will be an error. So don't put just 0. Rather, you can just a little you can have some little trick here. Let's put a very small value here, 0.000000, and this is just for reference. Okay, it's very close to 0. So actually we are having just a trick with CST, and we once we're done, press OK. We have to delete the results now. Well, again, I don't have the record for 50 ohm things, so I strongly recommend please save your work at every instance so that you can compare with the future results and the past results. Okay. So now that I can remember, pretty much the S11 was minus 21 or something, but I don't remember the S21. But there shouldn't be a problem. We can just compare the things, and I can just show you the things. It should be alright. So let's run the simulation again. Remember, this is for the short circuit thing. So let's have a look. The S parameter for short circuit impedance. You see, the value is pretty much messed up, and well, you can put your comments. Why is this happening? In fact, there is a question that change the impedance so that the load represents a short circuit. We have done that. After simulation, provide a figure. Why? Okay, provide a Smith chart for this. Okay, let's provide a Smith chart for this. You have to go to the 1D plot, click on the Smith chart. Okay, there we go. Okay, so you see that S11 49.71, S22, well, this is at home, and if you want to have a look at the value exactly at 1.5 gigahertz, now that you will need curve markers. At curve markers, double click on, press escape, double click on that marker again, 1.5, try to all. Well, this is for S11, this is for S22. If you need more, well, that's all, I think. 22. Okay, that's all. That's all you can see on the S1 and S22. So yes, so this is what you have to get. So the table says we are done with this value, short circuit. Okay, remember, you cannot get the value from a Smith chart for the case of S21 or S12. For that thing, you have to go straight away. There is parameter things, which is minus 90. It's going to be minus 90, so all same. That's your S11 value, that's your S22 value. Now you can repeat the same step, just change the impedance gain, the properties, define port. Now, the case of infinite impedance, which is open circuit, you have to put a really large value. Let's say 9000000 or something else. It's just funny. But anyway, we go. Let's run the simulation again. So we are done with the simulation for open circuit setup, and let's have a look into the S parameter now. Again, we are interested in S11 and S22 first. Okay, so you can note the value from here, and you see the 49.71 ohm, which is the our characteristic impedance ohms. However, and you see the value at 1.5 gigahertz. If you wanna go for the S21, you can get the value here. Well, it's pretty bad as a reflection coefficient, sorry, transmission coefficient. Yep. So a messed up situation, sort of a messed up situation once you are observing those parameters for the setup of short circuit and open circuit. But however, what could be the reason for this? Well, we'd be glad to hear from you. Just one hint, remember, it's all about impedance matching. The S parameter is closely related, closely dependent with the impedance setup, which you have already gone through a lot in your theory analysis or theoretical discussion. So, and remember, our target is that the sole reason of matching the impedance with characteristic impedance 50 ohm is that we want to maximize our transmission, whereas minimizing the reflection. Okay, so if you see something different apart from those things, that means you are having some issues with the impedance matching. Okay, so I hope you enjoyed today's lab, and I've tried my best to show the whole thing step by steps. But still, if you're having some issues with understanding, just let me know. We will try to get those done. Okay. All right. So thank you very much. We hope to see you in the next lab. Thank you.